test started. And just let me check it one more time. Okay, I think we are live now. Oops. Okay. So today we are going to start with the search algorithms. So if you have any problems with the data structures course or the search algorithms, I strongly suggest you to review them one more time. And today we are going to talk about the agents and the work of agents in the real life. So the basic thing we try to do for this course is, okay, for this class, let me draw it something like this. First, we start with the problem, okay? So we have something in the problem domain. Okay, so this might be any problem, like for example, you wanna play chess, or let's say taxi driver, or let's say another game or another problem. Okay, any problem in the problem domain. Okay, so first we start with a problem, and then we try to convert this problem into AI domain. Okay, so in the second step of our approach, we try to convert the problem into AI domain. Okay, so how can we handle this problem in AI domain, and how can we solve this problem in the AI domain? Okay, so this is going to be the question we ask, and this is the first time we are going to ask this question by using the search algorithm. So at the same time, we try to convert problem to AI domain means that we try to convert this problem into a search problem. Okay, and then on the final step, we propose a solution. Okay, propose a solution in AI domain. Or if we follow the same pattern in here, we also propose a solution in search algorithms. Okay, so here the only thing related, I mean, if you go for the boxes in below, the only thing related to the AI is the problem itself. Okay, so we don't provide anything special to the AI. Okay, but instead we try to solve the problem with using search algorithms, and in here, of course, the only thing related to the AI is the problem definition, coming back from the problem definition. Okay, so the problem is somehow related to AI. Okay, so basically the thing we are going to do for this class for today is bringing up some AI related problems, and then converting these AI related problems into a search problem and finding a solution in the search algorithms. Okay, so one more time, from the last week, maybe you remember, we have talked about the agents. Okay, and the agents have a planning domain on the background. We can use finite state machines, or we can use any reflex approaches for solving the problems, and then the agents are going to solve these problems. If you remember, for example, we have the reflex agents. They have if and else statements on the rule base, and then they do the exact action related to the environment, depending on the environment. Again, one more time, the planning agents have some simulations on the background depending on their engines, their state machines. Okay, and they can do some simulations like what if scenarios. Okay, so what about the search problems? How can we bring up a AI related problem into the search domain? Okay, so you perhaps remember the Pac-Man. If you don't, I strongly suggest you to play this Pac-Man game at least once in your whole life. And then we have a state of search space, and this search space is, for example, in this case, is 3 by 3. So starting from any point, this Pac-Man is gonna traverse the whole board in here, and then the optimum solution is traversing it with the minimum number of actions. Okay, so depending on your state, you can follow up into one of these state machine diagrams. Okay, so you start from the initial point in here. Okay, and then after you make a step to the north or east, you just transform into another state. Okay, so from one state to another state, we have transitions between these states, and then these transitions are creating the finite state machine. Okay, so again, one more time, the problem is converting the real life problem into a search domain problem. Okay, so let's think about a very famous example from our textbook. Okay, the same example appears in the textbook, and this is the map of Romania, and these are the cities of Romania. Bucharest is the capital of Romania, and let's say we are initially in Arad, okay, and we want to travel from Arad to Bucharest. And what is the optimal path to follow in order to reach from Arad to Bucharest? Okay, this is the question. Any of you have any idea about what might be the algorithm we are going to use for this problem?
Hocam, there might be an algorithm which starts with the shortest paths.
Exactly. So you know the shortest path algorithm. Shortest path is the name of the problem, but what might be the algorithms for the shortest path?
For example, to Arad to Bucharest, it may go to, is it 75 to Zerent?
Yeah, 75 to Zerent, 118 to Timisoara, 140 to Sibiu.
Yeah.
But did you ever heard about Dijkstra's algorithm? It's one of the shortest path algorithms, very famous one. But you're right, the problem is defined as shortest path. That's correct. And Dijkstra is one of these algorithms. Or maybe you can go for minimum spanning tree algorithms like Prims or Kruskal, or maybe you can go for minimum cut or maximum flow algorithms, depending on the problem definition in here. But these are some algorithms from the data structures courses. So one more time, if you have any problems in data structures, okay, I strongly suggest you to review these algorithms, and one more time read about them. Maybe if you have some codes from these classes, just review them and repeat them, okay? But anyways, it's not important for now. We have the problem in here, okay? We have the problem, this is the source. In some textbooks you can see it as a goal state. Bucharest is the goal state, or in some textbooks you can see Bucharest is the sink, source and sink, okay, or the target, okay. The terminology might change, but after all we have a clear problem definition in here. We want to make a traverse from we want to travel from Arad to Bucharest, okay. And here the search space includes the cities, and of course besides the cities we have the distances, okay, between the cities. Also we have a successor function, okay. Later on we will call this function as objective function or fitness function or goal state or performance function, okay. All these names are same for the same purpose. And here we have the roads, okay. So go to the adjacency with the cost, which is distance, and successor function, the success or the performance is going to be the minimum distance, okay. Okay, so this is going to be the goal state, goal performance. Okay, so we have a performance definition as the minimum distance. And also we have a starting state as Arad, goal state is the Bucharest, and we are looking for a solution, okay. So basically, by definition, this type of problem is a search problem, okay. So what can you do is you can start from Arad and go over all these possibilities to Timisoara, Sibiu, Zerent, Oradea, or other cities, and then search the minimum path, okay. So first you create all the possible travels to the Bucharest, and then you go for the minimum distance one, okay. So one more time, the search space is the number of possible moves you can do until you reach to the goal state, okay. So you start from an initial state and you have a goal state. So for example, for the Pac-Man, the goal state is beating all these dots, okay. So you beat these dots, you eat these dots, and when you complete eating all these dots, you win the game. So the goal state for Pac-Man is eating all these dots, okay, all these points on the screen in order to eat, okay. And you also need to escape from these animals, these aliens, and at the end we have a goal state, okay. So for example, a search space something like this could be calculated by using simple math. So you first calculate the possible options, but after from each state you can follow up to another state. So let's say you are starting with initially, let me draw it something like this. So let me give these numbers to the search space in here. Let's say this is the first line, and this is the second line, okay, third line, fourth, fifth, and sixth line. Okay, let's say we have 6 lines in the Pacman. Okay, so all these lines have the numbers, and also we can have these column numbers. Okay, 1, oops, and let's say 2. Okay, it's not gonna be a good drawing, but after all we can do this. I think 3, 4, and 5th column. Okay, so let's give numbers to these states in here. So Pacman is initially starting from, let's say, 4 to 5. Okay, so let me put it like this. So initial position of Pacman is, let's say, 4 to 4. Okay, just to make it easier, let's say it's initially starting from 4 to 4. And how many cells we have? 6 times 5 is 30 possibilities. Okay, so I'm just simplifying the problem. Okay, 30 dots initially. Okay, so all the move possibilities. So initially, let's say a Pacman can move to any direction like north, west, east, or south. So which makes that we have a search space something like this. Okay, so let's say initially we have a location like 4 to 4. Okay, and from 4 to 4, let's say we have 4 possible follow-ups. Okay, so this can be any of these follow-ups. Okay, so let's say if the Pacman travels to, let's say, which direction? Oops. Let's say if the Pacman travels to north. Okay, so this is gonna be 3 to 4. Okay, similarly, if the Pacman travels to, let's say, west, okay, then the coordinates of the state of Pacman is gonna be sorry, this is gonna be 4 to 3, but this is gonna be 3 to 4, right? Okay, and let's say similarly if the Pacman goes to south, okay, then this is gonna be 5, right? 4 to 5. Or let's say if the Pacman goes to east, then this is gonna be 5 to 4. Okay, so you see we have a state diagram in here just displaying the state of the Pacman, and from each of these nodes, of course we have other 4 possibilities. Okay, so for each one we will just continue with searching other options on the search space. So you see we are creating a search space in here starting from any initial node, and then all the follow-ups, and then all the follow-ups, and we are just creating a tree in here. Okay, so you know the trees perhaps. Tree is by definition DAG, which is directed acyclic graph. Okay, so even if we are playing a game, or if we have to complete a different algorithm, to complete a different problem, let's say like the taxi driver, or chess player, or any other game, let's say we have a search space, and then we can convert this problem into a search problem as displayed in here. And most probably all the graphs we created in here is going to be a tree. Okay, a directed acyclic graph by the definition. Okay, So safe passages. Can you find a safe passage, for example, in here? Any of you?
Is there any safe passage because the orange ghost blocks the big dot on the right to it?
Okay, so we assume all the aliens are staying still, they don't move. If they don't move, then we cannot find a safe passage here, right? That's correct. So the orange one is blocking one big dot in here, yes, correctly. If they move, but we can maybe have a very short time window in order to access this one. Anyways, good. So again, one more time, we are just converting a game, just like this one, into a search space like a tree, a directed acyclic graph, okay? So the search spaces can also be placed on this graph, okay? So you see, we have the initial state on the left-hand side, and then we have some movements, and depending on these moves, we have some states, and from each state, we have a follow-up state, and then we can create a graph like this. And in order to find the final path, it's exactly the same as a search tree, example in here, okay? So there is not much difference between the search space or a traveling problem in Romania, okay? So you start from a city and then you want to travel from cities to cities until you reach to Bucharest. Bucharest is the goal state in here, and Arad is the initial state, and we are just passing from one city to another city. Similar to this problem, we have an initial state in here, we have a goal state, and then we are passing from state to state until we reach to the goal state, and our purpose is reaching this goal state with the minimum number of moves, okay? So basically, we have the same approach, the same search approach for the games, for the real life problems, and so on, okay? So again, we have a state search, state space graph in here. So basically, we have some nodes indicating the states. We have the arcs or the edges or the arrows you see in the graph. They are the transitions from one action to another action. And we have a goal state which is indicated as capital G in here, okay? So we can use different notations in order to indicate the goal state and the initial states or the starting state, okay? In this notation, we are using the starting state as S and the goal state as the G, but in some other notations, maybe you can see different demonstrations. But after all, these are the state diagrams we use, okay? And for a tree, we have the search trees, okay? So here, for example, you see the direction of the movement besides of the score you have, because you have beaten one dot in this move, and then you can increase your score by 1. So in each transition from one state to another state, you can see we have the direction besides the score we gain from this move, okay? Later on, we are going to talk about these points, these punishments, and so on. But you can just create a search tree in here, and for the given state, the initial state, you can start making what-if scenarios. What if I move to the north? What if I move to the east? And so on, okay? So these are the possible moves you can do from an initial state. So the difference between the state space graphs and the search trees is the cycles, okay? So for example, in a state space graph, you can have cycles. On the other hand, in a graph, you cannot have a cycle. One more time, a tree is a directed acyclic graph. So initially, by default, the state space graphs have the directions. From one node to another node, you have a direction. For example, in the state space search, you cannot go from C to F, while you can go to F to C. So all these edges, all these transitions has a direction. Similar to the search tree. On the search tree, you can only visit from the topmost one to the bottommost one, okay? So you have a flow from top to down, and this flow is a natural direction. On the other hand, on the search space, we can have cycles, okay? So cycles are not forbidden in here, but for the search tree, we cannot have a cycle. So search trees are by definition acyclic graphs. Okay, so consider a four-state graph on the left-hand side. Okay, so these are the graphs I have added in the last class. So let me move them somewhere else. Okay, so don't consider these three in here. This is something I have created in last class. Hopefully I will move them now. Okay, so consider the graph on the left hand side. Okay, so this is a state space graph on the left hand side. Okay, so how big is the search tree if you convert it from this this tree in here? Okay, so if you start to create a search tree from the search state space graph in here, and if you want to create a tree from this graph in here, the graph size is going to be infinite. Okay, so because you have a cycle in here, you can see it. Okay, from A to B you can go to the B to A or A to B, so there is a cycle in here, and this cycle is going to be a tree like this. From S you can go to A, from A you can go to B, from B you can go to A, and it's going to be going like this until eternity. Okay, so we have an infinite loop, and by the definition we should say that the search tree which is going to be created from this search state space graph is going to be infinite. Okay, let me check if we are still streaming. Very good. Okay, this time I think it's working. Okay, so do you see the problem here, the recursion problem?
Yes, sir.
Okay,
It will go into the loop and will never end up.
exactly. So which one would you prefer? Which one is better for you, a state space graph or a search tree?
Search tree, according to my understanding, is better.
Yes, they have advantages and disadvantages. So for a search tree, it's easier to analyze it. It's easier to run some algorithms on it. So the algorithms are going to be much more simple than the state space graph. But on the other hand, state space graph is a little bit easier to create, to demonstrate the problems for human understanding. Okay, but for the computer processing we have problems in here. Of course we can handle these problems, but we are going to come this later on. But you're right, the trees has some advantages over the space graphs. Okay, again in here, for example, we can have some subtrees and levels in order to have the problem. So here you see this is an undirected graph, which means that from Zerent you can travel to Arad, from Arad you can travel to Zerent. Okay, so this is an undirected graph, so you can travel in both directions, and of course it might have some cycles. You can see any loops in here, any cycles in here, and if we try to convert this undirected cyclic graph into a search tree, which is a directed acyclic graph, so you are gonna start with drawing a tree like this. From Arad you have 3 possible follow-ups, and from each of them you can have other follow-ups, and you see from CBU you also have Arad as a follow-up. Okay, so again we have the same problem, from Arad to CBU, CBU to Arad, Arad to CBU, and it's gonna go on like this. Okay, so this is a problem. Okay, so how can we solve the problems like this? The first algorithm we are going to cover for today is the depth first search. Okay, so maybe we will cover 4 or 5 algorithms for today, and the first algorithm we are talking about is the depth first search. Ever heard about depth first search? Any of you?
Yes, sir, but can never remember.
Okay. In which class did you cover these topics?
I think data structures and algorithms.
Okay, exactly. So data structures is a very key class for today's course content. Anyway, so we have a tree in here. Okay, so this is a graph initially, let's say. So you see the starting node is given as S and the goal node is given as G. So from S to G, we are just gonna try to find a depth first search. Okay. So here we have a conversion from state space graph to the search tree. Okay, so you see from S we have two follow-ups, D and, oh sorry, three follow-ups, D, E, and P. Okay, so in the search tree, we also place these nodes as the child nodes. Okay, so again, we have the D, B, C, E follow-ups from D, and it's going on like this. And on the depth first search, we use a queue. Okay, so in the queue, let me just demonstrate it one more time in somewhere. Okay, so let's say we are going to use LIFO, last in first out. Okay, so last in first out means we are going to use a stack. Okay, so let's say this is our stack. I hope you know these terms, the stack, which is last in first out. And initially we are going to start with S. Okay, so on the bottom of our stack we have S as the value. Okay, and from S we can continue to three possible paths. Okay, so D, E, and P are the first possible follow-ups. Okay, so I'm gonna go with the D, E, and P in here. Okay, so from the S we can go on these values. But of course we have popped the S because we have visited S in this case. Okay, so stack has two possible functions, if you remember from data structures, pop and push functions. Okay, so pop removes one item from the top of the stack, push puts an item into the stack. Okay, so for example, initially, if you remember, we have only S on the stack. Okay, so if you pop the S value from the stack, you are going to remove it from the stack, and then you are going to put the possible follow-ups, which might be the P, E, and D. Okay, P, E, and D. Actually, the order of these three possible follow-ups is not important. So you can put P first to the bottom of the stack, or you can put D first to the bottom of the stack. But these three have no priority among them. Okay, so these are just randomly placed in here. And let's say this is the setup we have for the given problem. So the topmost one is the D. Okay, so from the stack we are gonna use the LIFO algorithm. Okay, so LIFO means that last in first out. Okay, so the last item we have placed into the stack is D. So the first item we are gonna pop from the stack is D, of course. Okay, so I remove the D, and instead I put all the follow-up paths of the D. So I have the B, C, and E. Okay, so you see the topmost one is E. So I'm going to continue with E and remove E, and instead of E I'm going to put H and R. You see, so from the R I'm going to remove R and put F. For F I'm going to remove F and put C and G perhaps. Okay, so you see this is one of the possible, and from G I'm going to remove the G. Okay, so up until this point, what was the path I have followed as a depth first search is I have started with S, and then I have placed D, E, R, and F, and G. Okay, so this is one of the possible paths for the depth first search. Okay, possible path for depth first search. One possibility of the depth first search. There might be other possibilities because there is no priority between the B, C, or E. So if you have the child nodes offsprings at the same level, then these nodes might have some, by the chance, might occur some different path possibilities. Okay, so for example, before E, maybe C can appear, which has no priority on top of E, and so on. Okay, so this is one of the possible paths the depth first search algorithm can generate. Okay, so again, we can use depth first search algorithm for reaching the goal state. But do you have any question about this one, or can you see any problems about depth first search? Any problems? Anything to ask?
No problem, sir.
Okay, you can understand this one, but if I say there is a problem with the depth first search, what would you say?
For example, if the solution goes from S and E, the depth first search algorithm had to calculate all the way through S to D tree way.
Yeah, exactly. So you say starting from S, maybe the depth first search is going to the D, and then instead of E, it's gonna go to the B, okay, and A. So let's continue this way, okay. So let me try to draw another stack in here, okay. So starting from S, let's say, okay, let's say initially we have the S on the bottom of the stack, and let's say S is the visited node. For DFC, let's say 2. Okay, so this is the second path. So we have S already on the path. And let me remove these things. Okay, so from the S, let's say we continue to D. You say it's D, right? And then from D, it's gonna, so we remove these items, of course. And then let's say it's, instead of E, we follow to the B, okay? Okay, so from D to B, this is one of the possibilities. Or let me put them this way, B, C, and E, okay? So this might happen in the stack, right? Okay, so last time, if you remember, we put these three nodes as BEP, but this time we have placed these nodes like ECB, okay? So you see, from the D, we can continue one of them, and let's say the topmost one is B. So I have removed B, and instead of B, I have placed A. So from the A, I have removed A, okay? By the way, the visited nodes in here are, let's say we have D and B and A, right? Because up until this point, we have reached the A. But from the A, we don't have any follow-up, and we still didn't reach to the goal state. So what's gonna happen is, we will just go one step behind and remove A in here and remove B in here, and then from D we will continue with the topmost one, which is C. So now the visited node is C instead of B, and here we also removed C, and instead of C we have A as a new node, right? From C we can continue to the A. And from C to the A, we also have another dead end, which means we need to remove A and C, and then go for, okay, A removed from here as well, and then continue with E as a possible path. And from E, we also have two possibilities, which are H and R, okay? And let's assume we have continued to the H, and then P and Q, maybe they didn't solve the solution, and then Q, no solution, and then R is a solution because we have handled the H side in here, and R, F, F and G, or CA, and then remove them and go to the G. Okay, you see, let's say by the chance we didn't get the correct path, we still can find a solution in depth first search. Did you get this part?
Yes, sir.
Okay. So any question about the depth first search? One more time. Okay. What is the problem with the depth first search? Can any of you say me a problem about the depth first search?
Excuse me, sir.
When there might be a problem with the depth first search, okay? So let's say I'm just claiming that, okay, there is a case, there is maybe a possibility for depth first search to not work, have a problem, okay? So can you see this problem?
If there is a loop going from one state to another and back to the previous state, and it will never reach the goal state.
Exactly. So if you have a loop, if you have a left recursion or right recursion, or let's say if you have a cycle, there might be a possibility, okay, we cannot guarantee it, but it's a possibility for having a recursion, having a loop, and never ending on the depth first search, okay? So we still don't have, because if you remember from our previous slides, okay, so if you remember, if there is a loop in the graph, we have an infinite, the depth of this tree, the search tree is infinite, okay? It's just going deeper and deeper. We cannot stop at any point, so the depth first search is gonna fail in order to find a solution or in order to reach to the goal state, okay? So this is a risk of the depth first search. Okay, so again, we are talking about a search algorithm properties, okay? So how can we classify the search algorithms? How can we methodologically approach the problems? The first thing we are going to talk is BIGO. Any of you know what is a BIGO, or worst case scenario, growth rate, complexity function?
I believe it's one of the ways we say, we rate the performance of the algorithm.
Exactly. So by using the BIGO, if you remember from the algorithm analysis or theory of algorithm classes, we have the BIGO, omega and epsilon values. So each of them are indicating the best scenario, the best case, the worst case, or the average case. So you either go for the theta or the epsilon or the BIGO, okay? They also have the smaller versions, so they are the upper bound or the lower bound in the complexity analysis, complexity functions, okay? But we have two different types of complexities. The first one is the time complexity, the second one is the space complexity. And you know, the computer science is the dilemma between the time and space complexity. So you can either have some benefits in the time by sacrificing something in the space, or vice versa, okay? So if we have some benefits, advantages in both of them, time and space complexity, you can forget the rest of the possible algorithms, okay? So we are always trying to find some benefits in time or space complexity. And again, in here, for the search algorithms, we need to know the depth of the tree, okay? So for example, in here, the pink points, okay, are indicating the goal states, and let's say the blue ones are the search algorithm, the reached nodes, the searched nodes, and B is the branching factor. So for example, the branching factor for the binary tree is 2, ternary tree is 3, okay? So it's going on like this. So how many number of branches, how many number of childs you can have from one parent node is the branching factor. And m is the maximum number of depth, okay? So for example, the number of nodes in the entire tree can be calculated, which is the worst case for any search algorithm, okay, can be calculated. Let's say we have initially one node as the root and b nodes as the second level, and b to the power of 2, or b square number of nodes as the third level, and it's going on like this, okay? So the total number of nodes we are going to search for this tree is going to be something like O b to the power of m, okay? So this is the worst case scenario by the complexity function, of course, okay? So the total number of values in here is not, of course, b to the power of m, but we have the O function, big O function, in order to calculate it. So if we follow up these complexity calculations for the depth first search tree, okay, so if we have a limit, the maximum number for the depth, let's say, we can have, and also we can reach the goal state later on. We are not sure about it, but we are going to touch to the depthmost node, at least for the left hand side here. So the total number of nodes we are going to go over is b to the power of m nodes, okay? And this is the worst case for the time and the space complexity, okay? So we need to create this number of nodes in order to make these calculations, and of course we need to make a calculation for the space complexity. But what if we try to optimize these values? For example, for the search time, maybe we don't have any chance, but for the search space, can we make some improvements? How can we have a better algorithm? Instead of drawing the whole tree, is it possible to draw only a line, a level? So let's, for example, okay, let's say this is the level n, and can I just trace this tree level by level like this, okay? So instead of drawing the whole tree, is it possible for me to just concentrate on one level and keep this level on the data, on the RAM, on the memory? And the answer, yes, please.
Hocam, breadth first search, I believe the answer. It searches in levels.
Exactly. So if you are going for the depth first search, you cannot go for the level. You cannot concentrate onto the level. Okay, so you need to go to the deepmost one first, like this. Okay, and then you can go to continue on to the next one, something like this. Okay, so depth first search is traversing the tree in this horizontal movements with the column wise approach. And you are right, if you want to go to the level by level approach, you need to go for the breadth first search. Okay, so again, let's remember the breadth first search, and let's just convert the same state search graph into a tree in here. Okay, and the search tree is going to have a queue. Okay, so first in first out this time, first in first out, which is a queue. Okay, and the queue has again the pop and push functions, but this time the pop function is popping from in front of the queue, and the pop push function is pushing from the back of the queue. Okay, so again here we have the same search tree, and instead of going to the S, D, E, R, F, G2, we need to first complete the first line like D, E, and P, and then go to the second line and then to the third line, and it's going on like this. Okay, so the breadth first search in this approach is going line by line. Okay, now again, if we continue with the same methodological approach, the breadth first search approach, the number of search, the worst case, let's say, if you have the goal states at the bottom, okay, so you are gonna search the whole tree, obviously. So this is the worst case, of course. So the big O calculation is, of course, O to the power of m again. But if you have a solution at some point on the tree like this, then you might be lucky, and this is not, of course, the big O, but the epsilon, the average case. You might have a better case like this. Okay, the worst case is always the first node you have as the goal state, but obviously we are not lucky that like this in the real life. So again, we have the b to the power of m as the big O for both cases. Okay, so let's ask you a question. When will breadth first search outperforms the depth first search? Any answers?
And there is a loop that prevents us from getting to the goal state in depth first search.
Exactly. If there is a loop, the depth first search cannot find even any solution. But let's say there is no loops in our graph. Can you imagine some cases the breadth first search outperforms the depth first search? Any idea? Sorry, one more time. Somebody talked about something, but I missed it. Okay, it's still streaming. Very good. So let's consider some cases like this. Okay, so let's say this is the search tree, and let's say this is the goal state. Okay, so this is the goal state. So let's say if the goal state appears in the top, which is the best case for both breadth first search and depth first search. So both of them has the same performance, right? both of them is going to find this solution at once. So there is no difference. Let me ask a case like, what if the goal state is somewhere like this? Which algorithm would you prefer?
Breadth first search.
Exactly. Why? Because breadth first search is gonna start searching and then is gonna go to one deeper state after completing all the states on this level. Okay, so it's gonna go on like level by level approach. Okay, but depth first search can start from the initial node and go directly to the deepest one and find this solution at once. Okay, so depth first search is better if the goal state is in here. What if the goal state is at the bottom right of the triangle? Which algorithm is better? I couldn't get you. There's a I think there is an echo on your computer. Are you together with one of your friends?
I'm not. It's Mohammed. Mohammed's
Anyways, the answer is there is no difference, right? Because after all, if this is the goal state, then both of the algorithms will search the whole tree, and then find the goal state. So there is no difference between breadth first search or depth first search. Okay, but what if the goal state is somewhere in here? Which one is better? Breadth first search. Exactly.
Breadth first.
Why? Because the depth first search is gonna go to the deepest one first and then continue on like this until reaching to this level. But breadth first search is gonna go on one by one. So maybe I can draw something like this. Oops. My computer is getting slower. At the same time it's streaming and recording and okay, so so I think we can draw something like this one in here. Okay, there is a limit in somewhere depending on the shape of the tree, of course. Okay, so let's put it in a blue or anyways. Okay, so there is a border in here. Okay, somewhere in here. We are not certain about the exact shape or exact position, but let's say there is a border in here. Okay, so up until some point, the breadth first search is better. From after some point, the depth first search might be better. After some point, they are equal to each other. Initially, they are equal, and then they are changing the advantages. Okay. And as a solution, which is the hybrid of the depth first search and breadth first search, we have iterative deepening search. Okay. So we have advantages from depth first search, we have advantages from breadth first search, but how can we use both of them at the same time? So as a solution, we have the third algorithm of today, which is iterative deepening search. In the iterative deepening search, you have a limit for your depth. Okay, so let's say we limit the first depth with the level 3. So the algorithm is using the depth first search again, but it's not going beyond the level 3. Okay, so it searches all the nodes until level 3, and after we reach to the level 3, if we are not lucky, if we haven't found the goal state yet, then the level is going to be increased to, let's say, 5. Okay, and then again the depth first search is going to be executed until the 5th level, and if there is still no solution, the depth is going to be iterated to, let's say, 7 or 9 or 10. Okay, so the steps can be calculated, can be optimized, but the algorithm's approach is just finding the limit for the depth first search and applying depth first search within the given limits, borders. Okay, so let's see. Okay, this is also the cost sensitive one. Okay, so this is the iterative deepening search. Another search algorithm is the cost sensitive search, and in here, instead of using the depth, okay, or the limit the depth, we go over the costs. So you know, we have the costs on the graph. If you remember the map of Romania, we have the cost as the distances because we try to find the shortest distance in here, so we need to calculate the costs. And the cost sensitive search in this case can be applied because there is a cost between these nodes, these travels, and cost sensitive search is just calculating the shortest path as we already told. And
excuse me, sir.
so okay, so one more time. Up until this point, up until to the iterative deepening search, we
Excuse me,
didn't.
sir.
You want to ask something?
Yes, sir. Sir, there is a problem in the connection and we are not seeing your screen
Oh,
from last 5 minutes.
okay. So let me. Yeah, maybe it's related with the internet connection, but in Discord something also is happening. Okay. I think. Okay, I have started the stream one more time. Can you see it now?
No, sir.
In Discord, you need to click the stream one more time. Can you see the stream one more time in Discord?
Sir, I think we should stop this streaming and join
Yeah,
again.
you should stop it and start to the new one. Okay, one more time. I'm stopping it. Please just. Okay, now starting a new stream. Okay,
Okay, sir.
just wait a second. Okay. Now I think it appeared, right? Just start.
Yes, sir.
Okay.
Yes, sir. That's okay now.
Okay, very good. Okay, so one more time, we were talking about iterative deepening search. So did you get this part, the iterative deepening search, how it works?
No, sir. Sir, kindly.
Okay, so the iterative deepening search is a mixture of the breadth first search and the depth first search. Basically, it's limiting the depth of the depth first search. So let's say if we have no limit in the depth first search, you know, we have the problem of the loops, right? It can go until the eternity. Okay, we can have the infinite loops just like in here, Arad to CBU, CBU to Arad, Arad to CBU. So it can continue like this. But in iterative deepening search, we first limit the depth and say, let's say the depth of the depth first search is going to be maximum 3, which means beyond this point, beyond the level 3, beyond the depth 3, depth first search cannot continue. Okay, if there is no solution until level 3, then the level is iterated one more time and the new level is, let's say, 5. And this time the depth first search is going to go until the level 5, and if there is still no solution, the level is going to be iterated. And it's iterated like this until there is a solution.
Okay.
Okay, so in each time the iterative deepening search is increasing the depth 1 by 1, or let's say 2 by 2, depending on the step function you have defined. It's just increasing, and then if you cannot find the solution, the depth is going to be iterated one more time. Do you understand the approach of the iterative deepening search?
Yes, sir. Sir, it is the mixture of depth first search and breadth first search.
Exactly. So you use the depth first search always. You don't use breadth first search. You use the depth first search. But the depth is iterated. The maximum depth is iterated, which is some approach similar to the breadth first search. Okay. For the cost sensitive search, we first need to define a problem with using the cost. Okay. So if you don't have any cost on your problem definition, then we cannot talk about cost sensitive search. So if you remember the problems in here, we are not talking about any costs from any node to another one. Okay, so all the problems defined here are just one step ahead from each other. Okay, so for example, from D to E, the cost is 1, okay, because we are just jumping from one state to another one, and we assume this cost is 1 initially. Okay, in the breadth first search or the deep first search, we have talked up until this point. But what if there is a cost on your problem, like the distances between cities, or let's say maybe you are just spending some money, you are playing on a financial stock market, let's say, and there might be some cost of the playing, or let's say you are just playing a gambling game and there is a cost, or playing chess and you are just scoring the points at the end, and so on. Okay, if there is a cost on your game or on your AI problem, then this type of problems are called as cost sensitive search. Okay, we need to provide a solution which is also taking the cost into account. Okay, we cannot think without the cost in here. So for example, if you remember, the search of the path from Arad to Bükreş was a cost sensitive search. Okay, so you see the difference between cost sensitive and insensitive search.
Sir, kindly repeat one time. It is a little bit
confusing. Okay, in your problem definition, okay, by the definition, if there is a cost of any move, okay, so for example, moving from Arad to Sibiu has a value here, right? 140. 140 is the cost from Arad to Sibiu. Okay, so this cost can be the distance, this cost can be the fuel consumption, time, any other thing. Okay, let's say in the chess, losing a piece might be a cost. Or let's say if you are a taxi driver and losing time is a cost, or earning money is a negative cost, and so on. Okay, so in your problem definition, if you have a cost, this type of problems are called as cost sensitive search.
Yes, sir.
Okay, and for the cost sensitive search, we need to provide another solution. Okay, so all the algorithms, okay, we have covered 3 algorithms up until this point. What were they? The depth first search, breadth first search, and iterative deepening search. Okay, for all these algorithms, we didn't take the cost into account. Okay, we only talked about the steps or the moves or the jumps, transitions between the states, but we didn't take the cost into account. But we have another algorithms. This is the 4th algorithm for today, which is called as the uniform cost search. Okay, in the uniform cost search, we have the cost on the graph, and these costs are also taken into account in the uniform cost search. And just similar to the iterative deepening search, we limit the maximum cost of the search. So for example, from starting point S, we travel to D, and then B, and then A, and the total value here is just reaching to, let's say, 15, or below, let's say this is the dead end because we cannot continue, but let's say we don't continue to C because it's beyond maybe 14 or 15. Okay, so we have a limit in here, and we just accumulate the total value up until any node, and then after we reach to, let's say, level 10, and then we can continue to 15, and then we can continue to 20 if we cannot find a goal state within the given borders. Okay, do you understand the approach in here?
Yes, sir.
Yes.
Okay, in the iterative deepening search, we were just iterating or limiting the depth by the number of moves. But here we have the costs, and we can put some limits onto the cost. Okay, just as in here. Okay, so in the uniform cost search, maybe depending on the structure of your tree, you can find a goal state just before reaching to the depth most state. Okay, so these four algorithms, the iterative deepening search, depth first search, breadth first search, has some advantages and disadvantages. We also have some videos, I think. Let me try to find them and show you. Okay, so this is the similar problem with the Pacman, and you see in the depth first search, so these dots, the white dots are indicating the search spaces. Okay, so starting from this green dot, initial square, let's say green square, it's just searching all the possible paths, follow-ups until reaching to the red one, and you see this one is finding a path from green to the red one. And let's see this one, another approach. Again, we are searching to the space, and you see we found a solution. Obviously, this is not the best solution, just as the previous one, but it's finding a solution with searching a less space. Okay, so let me ask your guess. What was the first search algorithm? This one, depth first search or breadth first search?
Is it breadth first search for example?
Exactly, because we have started from a certain point and we have searched all the you can think about like cycles in here. Okay, so just the closest ones and going on like this, and finding an optimal solution. But what about this one? Is it depth first search or breadth first search?
This is
One more time.
Depth first search.
Depth first search, exactly. So you see, maybe the half of the map hasn't searched, hasn't touched anything in the half of the map, and we found a solution without searching the half of the map. So the search time is much better than the breadth first search. We don't need to search maybe the bottom of this map anyways, but you see the solution we found is not the optimal one. Okay, so this is another risk in the depth first search. If you continue with the depth first search, you can find the solution, but you cannot guarantee it's the optimal solution, right? So do you understand the differences between breadth first search and depth first search?
Yes, kind of.
Okay, so let's see the uniform cost search this time. Okay, so it's just searching for all the possibilities in here and found a direct solution. So remember, uniform cost search is working like a breadth first search in here. What about this one? Okay. And let's go on like this. Okay. So
breadth first search.
this one is uniform cost search, and this one was the breadth first search. Okay, let me show you the breadth first search one more time. So this is breadth first search. Okay, so it's searching all the possibilities starting from the initial one and then trying to find the best solution. So you see the best solution is found with almost searching the whole map. You see white dots all around the map, and there is a solution in here. I'm not sure how optimal it is, but in the uniform cost search, obviously we are finding something not optimal as the breadth first search. Okay, but the search space of the uniform cost search is less than the breadth first search. Okay, so you see there maybe a portion of the map has not been searched anyways. Okay, depending on the cost. Okay, so in the uniform cost search, we have the limited approach to the search tree. You remember this graph in here? You don't go beyond some point if the cost is increasing. Okay, so in the uniform cost search, you see if there is some cost beyond the given function limit, then the algorithm is stopping searching this possibility. For example, maybe you can see the bottom corners, okay, left and right corners at the bottom. They have never been searched. Why? Because the total cost is so high for these points, and the algorithm is not going beyond this point, okay? And let's go for this one. What do you think about this search tree?
In the previous one, it had a better solution. It didn't exceed the cost limit. Why didn't it search for it?
Which one you see? Okay, so you mean this one?
The uniform cost one.
So this is the breadth first search. How many steps we have
the
to
uniform cost one.
the uniform cost? Okay. So
Doesn't it well, pretty much the same? No, it's shorter, right? If it goes to the right and then up and then right. So in the last portion of it, it goes 2 dots to the right. But it didn't search for the top right corner.
you mean the distance? Okay, can you see my cursor?
Yes.
Okay. So one more time, let's execute this one. Okay. Oh, I cannot show the cursor and the video at the same time. Anyways, you see that you say the top rightmost points, right? So depending on the shape of the maze, I think the distance is increasing for the search. Maybe we need to count the number of nodes in here, right? Maybe these gray, the light.
The fourth dot is the red dot, the red square, I mean. So it had a better solution, but it didn't even search for it. I don't understand why.
Yeah, I see. Maybe the light blue squares have less cost in here, or the darker ones have higher values, maybe.
Okay.
So depending on these costs, it prefers to going to the let's say inexpensive, the cheaper nodes.
Okay, I understand.
Okay, so I think that's all for today for the search algorithms. And one more time, this is the uninformed search. What is the difference between uninformed and informed search? We are going to talk about it later on in the next class, because now we have no idea for making any search. In this class, don't forget the most important thing we have covered is converting a real life problem into an AI problem or a search problem, okay? We didn't use anything related to the artificial intelligence, okay? We used something from your background, from data structures courses, the search algorithms. And these search algorithms can be applied to the AI problems. This is the most important thing we have talked today. So later on, we will just try to find some more intelligent, let's say, and tricky algorithms for finding these real-life problems. So the first thing we need to do is modeling the real-life problem in the digital world, in the AI world, okay? Any questions about the course content of today? Let me end the stream.